Stephen Hawking once noted that human curiosity is as boundless as the cosmos itself. I'm Mikhail, and I invite you on another cosmic exploration, which I trust will be both illuminating and calming. I appreciate you being here, and I hope you find this journey immersive. Our topic today touches upon something profoundly enigmatic. Not a story of a monster in the shadows or a far-off star, but an account of a fundamental restriction, a boundary woven into our reality. We will explore one of the universe's most recognized constants, the speed of light. More than that, we will contemplate the notion that something could move faster, not in a blatant or obvious fashion, but in a subtle way that currently evades our senses. The question I wish to explore with you today is this: is it possible that a velocity exists which surpasses that of light, but which we are simply unable to detect? This isn't a question meant to be answered with sudden clarity, but rather one to be considered gently, like a smooth stone you release into the calm surface of a deep lake. You can watch the ripples expand slowly, knowing you will never witness them all, as some are so fine and faint that they travel just beneath the surface in the realm of perfect stillness. This is our approach, to let these conceptual waves wash over us and give the question the space it needs to unfold. Let's begin with the very heart of this narrative, light itself. You have an innate sense of what it is, as it's the medium through which you perceive the world, and a prerequisite for your very being. Perhaps your room is dimly lit at this moment, with just enough illumination to trace the silhouette of furniture, or see the edge of a pillow. Or maybe the sole source of light is the display you are viewing. At its most fundamental level, however, light is not merely about brightness. It is, first and foremost, about movement. And this movement is so astonishingly rapid that, to our current knowledge, nothing else in the cosmos can outpace it. The velocity of light is roughly 299,700 kilometers per second, a figure that can feel abstract until you bring it to a more human scale. Consider that in the brief interval it takes for you to blink, a pulse of light could circumnavigate the Earth 7 times. A ray of light departing from the sun's surface requires about 8 minutes to cross the 150 million kilometers to reach our planet. If you were to aim a high-powered flashlight at the moon, its beam would strike the lunar surface in little more than a single second. This is the magnitude we are dealing with. It's not just fast, but an absolute cosmic limit established by the laws of physics. But how did we arrive at this understanding? To find the answer, we need to travel back to the early 20th century and the work of Einstein. In his special theory of relativity, published in 1905, he made a revolutionary assertion. The speed of light in a vacuum is constant, irrespective of the observer's own motion. This concept defies our everyday intuition, yet it marked a monumental paradigm shift in physics. Prior to Einstein, the scientific community presumed that light's speed, like any other velocity, was relative. For instance, if you're on a moving train, an approaching train appears to travel at a different speed to you than it does to a stationary observer on a platform. Light, however, operates differently. Whether you are in a spacecraft hurtling towards a light source or speeding away from it, your measurement of light's velocity will consistently be about 300,000 kilometers per second. Because this value is unchangeable, every other physical property must warp to preserve this universal law. This is the reason time slows for an object traveling at incredible speeds, and why distances contract for it. It is also the reason that, within our current physical models, Any object with mass can never reach, let alone surpass, the speed of light, as doing so would demand an infinite supply of energy. The closer a massive object approaches the speed of light, the more its own mass increases, which in turn requires progressively more energy for any further acceleration. It is a process akin to pushing against a wall that becomes heavier with each new effort, until eventually, even the smallest gain in speed would necessitate an unimaginable quantity of energy. And yet, this is where the puzzle becomes truly captivating. If nothing can travel faster than light, how is it that parts of our universe appear to be doing just that? The truth is, the notion of a cosmic speed limit is far more nuanced than it seems, depending entirely on what you are measuring. Consider, for instance, the expansion of the universe. You are likely familiar with the concept that our cosmos is growing, but this isn't like an explosion, where debris is flung outwards into pre-existing space. A better analogy is dough rising in an oven, with galaxies acting like raisins embedded within it. As the dough itself expands, the separation between the raisins grows, even though the raisins are not actively moving through the dough. And the most stunning realization is that some very distant galaxies are receding from us at velocities exceeding that of light. This might seem to contradict Einstein, but it doesn't, because his principle specifies that nothing can travel through space faster than light. When space itself is stretching, however, it can increase the distance between 2 points faster than light can traverse that same distance. No object is violating the universal speed limit. It's the very road beneath it that is elongating with each passing moment. This idea naturally prompts another question. If space can expand faster than light, might there be something else that operates by a different set of rules, moving in a separate lane altogether? Within theoretical physics, a specific name exists for such hypothetical particles: tachyons. If these particles were real, they would be defined by their inherent ability to always move faster than light, just as we are forever confined to speeds below it. Such entities would be permanently trapped beyond our cosmic horizon, making them not only unreachable, but effectively invisible to us. It's crucial to understand that there is no experimental validation for the existence of tachyons. While they emerge in certain mathematical frameworks, they remain theoretical phantoms. This concept, however, forces us to ask a more profound question. Is the speed of light the genuine ultimate velocity? Or is it merely the fastest phenomenon we are equipped to perceive? If something faster than light did exist, the most challenging part of the puzzle would be figuring out how we could ever know. Light is the fundamental medium through which we comprehend our world. We use it to survey the entire universe. All of our instruments, from telescopes to particle detectors, are built upon some form of electromagnetic radiation, be it visible light, infrared, or X-rays, and are calibrated for signals that move at or below light's speed. Any object moving faster would consequently outrun the very information that announces its existence, rendering it impossible for us to detect. This would be akin to trying to capture the echo of a sound before it has even been produced. Our tools, being finely tuned to the speed of light, would consistently find themselves lagging behind, unable to register a signal that has already passed them by. Perhaps other avenues exist for discovery, not through direct observation, but via subtle, indirect clues. We might find hints in the anomalous behavior of particles, or in mathematical models that only become coherent if we presuppose the existence of superluminal travel. It's possible the universe has concealed these phenomena from us, not because they are forbidden, but because they operate within a different coordinate system or another dimension, like a shortcut on a map that remains hidden from our view. Here, we are probing the very limits of contemporary physics, where concepts like extra dimensions and hidden variables start to surface. You can consider quantum entanglement, a phenomenon Albert Einstein famously described as spooky action at a distance. It involves two particles becoming linked so that assessing the state of one instantaneously influences the other, even if they are separated by light years of space. While this does not permit the transmission of messages faster than light, it certainly prompts us to question how information can be so flawlessly correlated without any travel time. The solution may not lie in surpassing a speed limit, but rather in discovering an entirely different method of connection, one that doesn't involve racing through space, but instead makes the journey itself unnecessary. This isn't a science fiction trope about teleportation. It is an acknowledgement that our grasp of speed, distance, and causality might just be a local phenomenon, true for our particular layer of reality, but not for the universe as a whole. This is an idea worth contemplating, not in a hurried search for a simple answer, but by allowing the concept to settle and grow in your mind. Despite its breathtaking velocity, light may not represent the final chapter of this cosmic story. There could be a more fundamental structure to reality that we have yet to encounter, not due to a lack of intelligence, but because our exploration is limited by the senses and instruments available to us. Right at this moment, wherever you happen to be, photons from stars so remote that their light started its journey long before humanity appeared on Earth are silently traversing the immense void. They arrive precisely on schedule, governed by their own physical laws. Yet maybe something else exists, something that requires no time for its passage, something that was already here even before that ancient light departed from its star. The mere possibility of this is enough to make one's heart beat faster with curiosity. Let's pause on this idea for a moment. The speed of light is far more than a dry figure in a physics textbook. When we discuss it, we are touching upon something much deeper. We are talking about the very possibility of seeing, of knowing, and of remembering. Light acts as the cosmic courier, delivering news from the most distant regions of the universe, news that invariably arrives late and carries with it the echoes of long-vanished events. The single thread that connects us to the cosmic past is, in essence, a beam of light reaching our eyes or our instruments, our sole proof that anything is happening out there at all. And yet, for all its astonishing speed, light might not be the only mode of interaction within the cosmos. Typically, when you and I think about speed, we envision traveling from one point to another. But what if a connection could be established without any movement at all? What if a link could be genuinely instantaneous? This is where quantum physics and its perplexing puzzles come into play, particularly the phenomenon of quantum entanglement, which suggests two particles can perfectly mirror each other's states regardless of their location, with no delay and no signal traveling through the space between them. Most physicists concur that this strange correlation doesn't allow for information to be sent faster than light, but its existence compels us to reconsider what movement truly signifies in the quantum realm. Is the speed of light an absolute restriction on all forms of motion, or is it merely the boundary for a specific kind of physical interaction? We will circle back to this fascinating question, but to seriously entertain anything moving faster than light, we first need to deepen our comprehension of light itself. Einstein revealed that this speed is intrinsically woven into the very fabric of the cosmos, explaining that space and time are not distinct arenas for events, but a single, malleable entity known as space-time. The speed of light is not simply a rule imposed upon this fabric. It is one of its inherent properties, much like the fixed tension of a guitar string or the boiling point of water. It is not merely a number, it is the fundamental shape of our reality. This implies that if we ever manage to discover something that genuinely, not just in theory, surpasses this velocity, we will be confronting a phenomenon far more profound and bizarre than we can currently conceive. That moment, however, has not yet come. Until it does, our guide remains light, which serves not just as something we see, but as the universe's ultimate standard-bearer for speed. There is an almost mystical quality to the fact that light has a limit. If anything in the universe ought to be entirely unrestrained, it should be light, which possesses no mass, requires no fuel, and travels without any external push. While light certainly transports energy, its movement generates absolutely no friction or resistance, resulting in a state of pure, perpetual motion. Despite this, its velocity is rigidly set at a particular value, roughly 300,000 kilometers per second. It never travels even slightly faster, a constant that is repeatedly confirmed in the functioning of everything in existence. So why is light prohibited from exceeding this velocity? To uncover the reason, you must let go of your conventional understanding. Our intuition tells us that speed can always be augmented by simply pressing the accelerator harder, applying greater force, or sustaining the push for a longer time. This principle holds true for everyday objects like a car, a runner, or a stone you've thrown. But such logic completely unravels when velocities approach that of light. As an object travels faster, accelerating it further requires an exponentially greater amount of energy. Crucially, the more energy you invest, the more massive that object actually becomes. This concept is not some poetic flourish, but an unyielding law of physics. Within the framework of relativity, energy and mass are essentially two expressions of the same underlying entity. Therefore, the more kinetic energy something possesses, the larger its effective mass becomes. To illustrate, consider the act of pushing a cart. Initially, the task is simple, but as it gathers speed, it begins to feel as if it's being filled with heavy lead. You aren't merely boosting its velocity. You are simultaneously increasing the very difficulty of accelerating it any further, dragging a heavier and heavier load with each push. As you get closer to the speed of light, this metaphorical weight doesn't just increase, it skyrockets toward infinity. Infinity isn't just a very large quantity. It represents an insurmountable physical boundary, as no engine or fuel source can supply an object with infinite energy. Such a feat is impossible in both theory and practice. However, the most fascinating aspect is that light doesn't even attempt to attain this speed. It doesn't have to strive for it, because it always exists at this velocity. This is because photons, the fundamental particles of light, possess absolutely no rest mass. Consequently, they are not accelerated to the speed of light, but are instead created with it. Every photon that has ever come into being has perpetually moved at this exact speed, never varying. It is their inherent and only possible state of being. You cannot slow a photon down to a standstill and place it on a shelf. It can be absorbed, reflected, or refracted, but it can never be made motionless, as it has no state of rest. Its very essence is motion, which always proceeds at that unalterable velocity. This particular characteristic endows light with a fundamental consistency that few other phenomena can rival. Regardless of your location, your direction of gaze, or the speed at which you are moving, light will always advance toward you at the same constant velocity. This isn't merely a convenience for calculating cosmic distances. It is essential to the very structure of physics itself. This unwavering speed gives us a universal benchmark, a standard that remains independent of the observer. Without such a constant, time would behave erratically, events would lose their coherent order, and the relationship between cause and effect would blur into an unpredictable haze. Because the speed of light is fixed, we are provided with a coherent framework, a structure for reality itself. This universal speed limit isn't an arbitrary rule. It's not as if there's an unseen barrier. Rather, the very fabric of space-time is woven in such a way that this velocity represents the ultimate boundary of what is possible. It is comparable to the maximum volume a string can emit before it breaks, or the highest rotational speed a wheel can endure before disintegrating. The limit is not a restriction, but a physical outcome of the system's intrinsic properties. Once you grasp this, you start to see why this specific number is so central to our understanding of the universe. As you approach this ultimate speed, time itself begins to slow down, space contracts, and mass escalates. Einstein's famous equations do not describe what light desires, but rather what befalls everything else that attempts to pursue it. Light itself remains oblivious to these effects. From the viewpoint of a photon, if one could even possess a viewpoint, zero time elapses between its creation and its absorption. For the photon, the entire expanse of its journey unfolds in a single, timeless instant. It doesn't experience space as we do. There is no perception of flying through a void. It simply exists in motion at the only speed it can ever have. Here we encounter one of the most profound paradoxes of physics. To us, as external observers, light journeys across vast distances, a process that requires time. Yet for light itself, if we could adopt its perspective, there is neither distance nor time, only a beginning and an end that emerged into one. This, in a way, only serves to highlight how profoundly constrained our own perception of the universe really is. Imagine for a moment that our entire reality functions with a slight but unavoidable delay. This is not a flaw or a bug in the system, but a foundational quality of the world we inhabit. We are entirely accustomed to it. The sound of thunder arrives moments after you see the lightning flash, because sound waves take time to cross the intervening space. Even our own thoughts, which are nothing more than swift electrical signals firing between our neurons, are not genuinely instantaneous. They travel at tremendous speeds, but these speeds are not infinite. Every sensation you register is actually a glimpse into the immediate past, even if only by a tiny fraction of a second. Every observation you make is a recording of something that has already happened. Seen this way, the speed of light transforms from a mere constant in a physics textbook into the absolute horizon of our perception, the very limit of the knowable world. What would happen if something could travel faster than light? You wouldn't just be unable to catch it, you would be entirely unable to see it, as it wouldn't reflect any light toward your eyes. You couldn't hear it, since sound is vastly slower. It's conceivable that we couldn't even confirm its presence with any of our instruments, unless it left behind some kind of indirect spectral evidence, a sort of ripple in the fabric of space-time. This is precisely why physicists hold this cosmic speed limit in such high regard. The critical question isn't how fast something can travel, but rather what is fundamentally accessible to our observation, and what can be considered a part of our shared reality. Of course, science fiction and speculative theories are constantly proposing ways to circumvent this fundamental limitation. You've likely heard of concepts like wormholes that fold the fabric of space, warp drives that contract it ahead of a starship, or even theoretical tachyons, which are particles for whom moving faster than light is their only state of being. Yet, it's important to recognize that even these imaginative ideas don't try to blatantly break the universal speed law. Instead, they seek out potential loopholes, proposing not to just accelerate harder, but to fundamentally alter the map of reality on which we travel. This cosmic speed limit is profoundly integrated into our entire model of the universe. Think about how even our definition of the meter, the fundamental unit of length, is now tethered to the speed of light. As of 1983, a meter is formally the distance that light covers in a vacuum in 1/299,792,458th of a second. We no longer use a ruler to measure light. We literally construct the ruler from light's own velocity, which shows just how essential it is. Imagine if the speed of light were to abruptly become unstable. Our whole framework of measurement, along with all of modern engineering and cartography, would instantly fall apart. The advanced technologies you rely on every day are founded upon this unyielding constant. Your GPS, for instance, must synchronize with numerous satellites with nanosecond accuracy, a feat only possible because the speed of light is so dependable. The smallest fluctuation would be enough to direct you to an entirely different town when you were just looking for the nearest coffee shop. When we speak of light having a speed limit, we aren't complaining about some cosmic failing. Rather, we're acknowledging its central role in the architecture of reality. This constant serves as both the unbreakable ceiling above us and the very foundation beneath our feet. This understanding brings us to an even more profound truth. A universe with a speed limit must also have a limit on influence. No action can produce an effect anywhere else in the cosmos instantaneously. You can't simply will a distant planet to alter its orbit at the very moment the thought occurs to you, because even gravity, which feels so immediate to us here on Earth, must travel at the speed of light. When a pair of black holes collides billions of light-years from us, the gravitational waves from this monumental event don't arrive at our instruments in an instant. These ripples journey across the cosmos at light speed, meaning we only register the cosmic echo of this event millions of years after it is actually finished. This inherent delay is not a system flaw but a fundamental design feature of our universe, a property that is simultaneously humbling and magnificent. Living in such an immense cosmos, we are fated to only ever observe the past, with countless events having already occurred that we either missed or will never get to see. Light does its absolute best to deliver the news, but even its capabilities have their boundaries. There is something deeply beautiful, if a bit unsettling, in this realization. Every single photon striking your retina, each particle of light that warms your skin, has completed an extraordinary voyage across the void just to reach you. That particle has traveled without rest or pause, rigidly obeying the universal speed limit, all to convey a message not with words, but through its simple arrival. Proof that something happened long ago and far away, and that you, in this very moment, are the final destination of its grand journey. Have you ever stopped to consider why light even has a specific speed limit? The answer may not be a matter of simple physical restriction, but may lie in the very essence of the universe itself. It's as if the cosmos requires a conductor to set the tempo for all of existence. This limit isn't a barrier, but a foundational rule that separates what has already entered our reality from what is yet to unfold. Within this cosmic punctuality, there is a profound harmony, and who can say what greater melodies might exist beyond this rhythm, waiting for our instruments to finally tune in. When you hear the word speed, your mind probably jumps to the simple formula from school: distance over time, like a car moving at 100 kilometers per hour, or a sprinter covering 100 meters in 10 seconds. This apparent simplicity, however, is merely the surface of a concept with astonishing depth. If you look closer, speed is less about an object getting from point A to B, and more about its intricate relationship with the very fabric of existence, a complex interplay of space, time, and your own point of observation. This leads to a critical question. What are we measuring speed in relation to? In any absolute sense, nothing in the universe is truly at rest. When you clock a train at 100 kilometers per hour, you are measuring it against the tracks. But those tracks are on Earth, which is spinning on its axis while simultaneously orbiting the Sun at nearly 30 kilometers per second. Our Sun is journeying through the Milky Way, and our galaxy itself is hurtling toward Andromeda. The true speed of that train, therefore, is an illusion. It simply has no absolute value. Everything hinges on the frame of reference you decide to use, creating a kind of matryoshka doll of perpetual motion, where every reference point we assume is stationary is itself moving within an even larger system. As far as our current understanding goes, this principle has only one exception: the speed of light. Its velocity is absolute and constant. It doesn't matter where you are or how fast you're moving, light will always race past you at the exact same speed. For everything else, velocity is always a question of perspective. So, what is the ultimate implication of all this for us and for the nature of light itself? At its most basic, speed is just the rate of change in an object's position through time. The real challenge is that the very concepts you take for granted in daily life, position and time, are nowhere near as stable or constant as they appear. They are, in fact, part of the same dynamic cosmic dance dictated by the one true constant we know. You're probably accustomed to viewing space as a fixed three-dimensional grid, with time being a universal current that flows identically for all people in all places. However, a century ago, the theory of relativity demonstrated just how profoundly wrong that intuition is. Space isn't flat. It possesses the ability to warp and bend under the influence of mass and energy. Likewise, time isn't absolute. Its passage can be stretched or compressed. They are not distinct entities, but are interwoven into a single, four-dimensional fabric that we know as space-time. Within this continuum, your speed is not merely movement across a grid, but a form of navigation through the very structure of existence. And light establishes the universal benchmark, defining the ultimate trajectory possible. Picture space-time as an immense, taut rubber sheet. A massive body, like a planet or a star, presses down on this sheet, creating a depression that distorts it. Any object with mass that travels across this surface is compelled to follow its contours, and light simply takes the most direct and thus the quickest possible route through this warped geometry, a path that nothing with mass can ever beat. This inherent cosmic speed limit is why the speed of light materializes in equations that seemingly have no connection to light itself. It appears whenever the principle of causality is involved. If anything were capable of moving faster than light, the fundamental logic of the universe would disintegrate. The sequence of events, in which a cause must always come before its effect, would be completely ruptured. This would be as nonsensical as getting a response to an email you haven't sent yet, or feeling the warmth of a fire you have yet to start. Such a scenario is more than just an imaginative absurdity, as traveling faster than light would be tantamount to moving backward in time. The universe, it seems, has a profound aversion to these kinds of paradoxes, and is built with reliable safeguards against them. Setting aside the complexities of advanced physics for a moment, speed is also a matter of your personal perception on a more intuitive, human level. You don't register it as a digit on a display, but as a rich sensory input, from the blurred shape of an object racing past to distinct changes in sound pitch. Think about how the siren of an ambulance shifts in tone as it approaches and then moves away from you. This is the well-known Doppler effect. Your brain interprets these signals to construct a feeling of motion. Yet, your perception of speed is remarkably selective and constrained. You are entirely unaware that our planet is hurtling through space at over 100,000 kilometers per hour. To you, it feels like perfect stillness. Motion only becomes apparent when you have another object to serve as a point of reference. This inability to sense grand velocities makes the entire idea of faster-than-light travel even more perplexing. How would you even go about detecting it? If an object were to exceed the speed of light, any information about it would arrive in a jumbled sequence. You would witness the consequence of its action before you observed the cause. It would be like seeing a glass on a table shatter into fragments and then, a moment later, seeing the stone that broke it flying through the air. Your world would effectively become a film running in reverse. So, you can see the speed of light is not so much a cosmic cage as it is the very grammar of the universe, the set of rules that ensures its story unfolds in a coherent and logical way. And while we have never picked up any signals that defy this boundary, we continue to monitor the silence. It is in that vast unknown that the solutions to our deepest questions might just be waiting. What exactly is speed? The conventional answer, distance divided by time, seems straightforward enough. Yet, if you probe more deeply, that simple equation collapses, unveiling a reality teeming with paradoxes and astonishing insights. Things take a particularly bizarre turn in the quantum universe, where at the scale of elementary particles, the familiar concepts you depend on simply stop working. A particle lacks a definite position or a specific speed until you make the decision to measure it, existing instead as a wave of pure probability, a hazy cloud of endless potential. It is only in the act of observation that you essentially compel the particle to commit to one particular state. But between those measurements, the very idea of speed becomes meaningless. An electron's movement is nothing like the predictable arc of a thrown stone. It's more of a flicker between numerous possible paths, only one of which becomes real when you, the observer, intervene. This surely makes you reflect on your own role in the cosmos, suggesting you aren't just a passive witness to reality, but an active participant in its creation. So, what truly defines the essence of speed? I believe it's a sophisticated blend of several elements. On one level, it's rooted in the fundamental interplay of space and time, the material from which our universe is constructed. On another, It is a product of our measurement techniques, our instruments, and our definitions. And a third component is perhaps just a mirror of our own cognitive limitations, our human tendency to simplify and categorize the world around us. But there is one more equally fascinating way to look at it. Speed is not just a measure of how quickly an object travels through space. It's also about the rate at which information can propagate, and causality itself can be conveyed. This perspective explains why the speed of light occupies such a foundational role in physics. The crucial point isn't that photons are uniquely fast, but that their speed represents the absolute limit for any signal, influence, or cause to travel through the universe. For instance, if you push one end of a long steel rod, you might assume the other end moves at the exact same instant. But that's not what happens. The information about your push, the compression wave, moves through the metal at the speed of sound for that material. A wooden rod would transmit it more slowly, and air more slowly still. The speed of light is the ultimate boundary for the propagation of any cause. And if information could be sent faster, it would destroy the logical underpinnings of existence, allowing you to get an answer to a question before you even thought to ask it. Such an occurrence would lead to temporal paradoxes, unraveling the very fabric of cause and effect. Although we lack any solid experimental proof for this possibility, even the perplexing marvel of quantum entanglement fails to provide a loophole. In this phenomenon, two particles act as a unified system irrespective of their separation, yet this doesn't enable the transmission of information beyond the speed of light. While their connection appears instantaneous, you cannot use it to convey any meaningful data. This reality compels us to ask if another form of velocity might exist, one not bound by this ultimate restriction. It might not be a speed of travel in the traditional sense, but rather a speed of connection, a quality that doesn't need to traverse space because it is intrinsically present everywhere simultaneously. Certain physicists delve into these concepts, employing ideas like a unified quantum field, or the theory that space-time itself is an emergent quality of something more fundamental, existing outside our familiar concepts of distance and time. For the present moment, however, these ideas remain purely speculative, and the speed of light continues to be our definitive benchmark. We gauge all motion, from a leaf drifting across a pond to a starship bound for distant galaxies, by measuring it against this absolute standard. But if you pause to consider it, speed represents only one part of the picture, with time being its equally vital counterpart. Without the progression of time, the notion of speed itself loses all meaning. You can't describe something as fast or slow without a before and an after. Our entire framework for motion hinges on how we perceive and quantify the passage of moments. And it is here that the theory of relativity reveals another startling fact. For any object in motion, time itself slows down. This demonstrates that speed isn't merely a figure on a display but a deeply personal experience. The most rapid things often go completely unnoticed, passing through our lives without leaving any mark. They are silent and imperceptible, like a soft breeze that barely stirs a curtain, or a shadow that glides over a wall when no one is watching. There is a deep truth in this idea that genuine motion doesn't need to announce itself, as not all velocity has to be forceful and loud. Light serves as the perfect illustration of this principle. It produces no sound as it traverses the cosmic emptiness and doesn't disturb the air like a sonic boom. You will never hear its approach. It simply arrives, filling the space around you. Even after journeying for millions of light years, it leaves no destruction in its wake, embodying a perfectly smooth and silent movement. And what should we make of shadows? A shadow is not an object, but simply the absence of light. And while it appears to move, its motion is of a unique nature derived from the movement of other things, namely a light source and the barrier obstructing its path. Here is a truly remarkable concept. Under specific circumstances, a shadow can actually travel faster than light. This doesn't happen because a physical entity is breaking the cosmic speed limit, but because a shadow lacks mass, carries no information, and is therefore not constrained by the same physical laws. To understand this, picture a powerful spotlight aimed at a faraway surface, like the face of the moon. If you were to flick your hand quickly across the beam, its shadow would streak across the lunar terrain at a velocity far greater than light speed. This presents no paradox and violates no physical law, because no material substance is actually journeying from one side of the shadow to the other. It is just a geometric illusion, a series of shifting projections. The same principle applies if you were to sweep a laser pointer rapidly across the moon, as the red dot's seemingly superluminal speed is just the new position where photons are striking at each instant. These illustrations help us grasp the essential difference between objects that are truly in motion and those that only appear to be. Physics is concerned not just with an object's velocity, but with whether its movement can transport energy or information, and thereby influence or enact change. This distinction deepens when we consider space itself, which is not a passive backdrop for events, but a dynamic medium that can stretch, compress, and warp. When a colossal event like the collision of two black holes occurs, gravitational waves ripple through the fabric of reality, causing space itself to expand and contract, a kind of motion utterly unlike any other. Ultimately, the most magnificent example is the expansion of the universe. Far-off galaxies are receding from us, with the most distant among them moving away at speeds exceeding that of light. This, too, breaks no rules, because the galaxies are not hurtling through space. Rather, the very expanse of space-time between us and them is stretching, carrying them along like dots on the surface of an inflating balloon. Because of this accelerating expansion, the light emitted by these galaxies will never manage to reach us. These cosmic bodies are forever concealed behind our cosmic horizon, an invisible threshold beyond which no signal can ever arrive within the universe's lifetime. It's not that we cannot see them now. It's that we will never be able to see them. This incredible phenomenon is a profound reminder that speed is about far more than the simple movement of objects through space. It is a fundamental key to comprehending the nature of reality, time, and our own perception of the cosmos. At times, the most profound transformations unfold silently and relentlessly, much like an unseen current. This concept of a quiet wind isn't merely a poetic device. It serves as a near-literal depiction of our reality. There are processes and forces at play that shift entire galaxies, yet they operate in total silence, generating none of the effects you might expect. They don't defy the laws of physics or draw attention to themselves. They just are, and they act. Even light, the very benchmark of velocity, is entirely soundless. You will never be able to hear a light beam as it approaches. Sunlight traverses millions of kilometers of empty space to reach Earth without making a sound, bathing our world in warmth and color while possessing no voice of its own. Sound emerges only when light's energy is converted into another form, such as the whisper of leaves warmed by its touch, the faint crackle of asphalt on a summer day, or our own voices, which we hear while seeing the person we're speaking with. This presents a paradox. The fastest phenomenon we know is also the most silent. But its silence is a powerful form of presence we're not conditioned to recognize. This all leads us to wonder if our perception of speed is too simplistic, perhaps constrained by the limits of our senses and our instruments. We can only gauge the things we can directly interact with. But what if the cosmos contains different types of motion we are currently unable to detect? This doesn't mean particles breaking established laws, but maybe the movement of space-time's fabric itself, shifts in cosmic relationships, or the flow of information without any physical carrier. Of course, investigating something you cannot catch is an incredibly difficult endeavor. Yet the entire history of physics is a quest to find the invisible by studying its traces. Scientists meticulously observe effects, measure tiny deviations, and analyze the resulting consequences. You can measure the influence of a shift even if you cannot see its cause, which is why the search persists. Physicists are not hoping to discover a particle moving at twice the speed of light, but they acknowledge that our model of the universe is far from complete, leaving room for new kinds of motion, and perhaps entirely new definitions of speed itself. We tend to envision light as the undisputed champion, the perpetual victor in the cosmic race, leading the way and serving as our ultimate measure of space and time. The very thought that light could fall behind anything, even for an instant, feels profoundly unnatural. Under specific circumstances, however, this is precisely what occurs. The fact is, light doesn't consistently travel at its renowned maximum velocity of approximately 300,000 kilometers per second. It only achieves this speed in the pristine void of a perfect vacuum. As soon as light passes into any medium, be it water, glass, or even the air around you, it begins to slow down. This might sound peculiar, as the beam from a flashlight appears instantaneous to our eyes, but the reality at a microscopic scale is far more intricate. While journeying through matter, light is in constant interaction with it. Picture a runner trying to cross not an open field but a packed crowd. Their average speed would plummet as they are forced to weave and navigate. The same principle applies to light, which moves at roughly 3/4 its maximum speed in water, and even more slowly in glass, a property that allows lenses to bend and focus its rays. This brings up a frequent misunderstanding you should avoid, which is the idea that individual photons, the particles of light, are actually stopping and starting again. The truth is much more subtle. Light, exhibiting properties of both a wave and a particle, engages in a collective dance with the atoms and electromagnetic fields of a material. This interaction impedes the free propagation of the light wave, causing its leading edge to lag. Scientists have even learned to trap light, using complex quantum optics to slow it to the pace of a person walking, and in some cases to freeze its information in a cloud of supercooled atoms before releasing it again. Even in these extreme scenarios, the universal speed limit, the velocity of light in a vacuum, represented by the letter c, is never broken. This brings us to a fascinating question. If light itself can be slowed, is it possible for something else to overtake it? The answer is yes, and a prime example is found in nuclear reactions. Within a specific medium, like the water used to cool a reactor, a charged particle can travel faster than light does in that same environment. To be clear, this is not faster than the absolute cosmic speed limit, only faster than light's local, reduced speed. When this occurs, the particle emits a captivating and almost otherworldly blue luminescence known as Cherenkov radiation, which is essentially the optical equivalent of a sonic boom. Another remarkable illustration comes from the field of astronomy. When massive stars detonate in supernovae, they release not just light, but also neutrinos, which are tiny, ghost-like particles that pass through matter almost completely unhindered. As a result, when a supernova occurs, the neutrinos escape its core and race outward, while the light must battle its way through the dense, superheated material of the exploding star. Consequently, the neutrinos often arrive at our instruments first. When we witnessed the supernova in the Large Magellanic Cloud back in 1987, our detectors here on Earth recorded a massive influx of neutrinos several hours before our telescopes could register the initial burst of visible light. This event offered definitive proof that, under the right conditions, even the universe's ultimate speedster can be beaten to the finish line. The cosmos announced this monumental occurrence not with a brilliant flash, but through the nearly undetectable whisper of its most elusive particles. This compels you to contemplate a far deeper concept: the very mechanism of transmitting information. Among theoretical physicists, discussions are ongoing about what truly defines a signal, how it propagates through the void, and what even constitutes a complete transfer of data. We are aware of laboratory setups where pulses of light travel through specific materials in ways that seem to violate every known principle of logic. The peak of one of these pulses can emerge from the material before it has technically even entered, a phenomenon referred to as superluminal group velocity. But you should not rush to judgment, as the fundamental law of the universe holds true. No actual information is moving faster than light. In essence, this is a fascinating mathematical curiosity, almost a form of optical illusion, that stems from the distinct behavior of wave packets within specialized media. If you were to track each individual photon that comprises the pulse, you would find it still adheres to the cosmic speed limit. Nevertheless, the mere possibility of such effects raises some challenging questions about what else might be capable of this, if light patterns can seemingly outrun themselves, and whether there are methods of motion we have yet to grasp that aren't reliant on particle movement as we understand it. As of today, there is no credible evidence suggesting that matter or information can breach the light-speed barrier, with every single confirmed experiment and observation reinforcing its unshakable nature. Yet, we frequently encounter situations where light, the undisputed champion of speed, does not always prevail. Other phenomena, like neutrinos that barely interact with anything, or shock waves from cosmic explosions, can actually outpace a light beam that is struggling through a dense medium. Therefore, while light formally remains the fastest thing in existence, it doesn't always win the race, deliver the clearest signal, or arrive at its destination first. The fact that light can be delayed prompts you to wonder what this implies for our grasp of space, time, and the sequence of events in a cosmos where we depend so heavily on light as our main informant. Every variation in its journey becomes exceptionally compelling. Perhaps light's most remarkable quality isn't its ultimate velocity, but what you might call its persistence. It doesn't clamor for your attention or insist on being first. It simply continues along whatever route is open to it. It may sprint through a vacuum, patiently navigate obstacles, or find an alternate path when blocked. And upon its eventual arrival, it always delivers a narrative from a different place and a different era, a faint echo of an event from the distant past. When you delve into the cosmic speed limit, you are inevitably led to its most awe-inspiring manifestation, a location where this limit becomes an absolute, inescapable boundary. This place, a kind of perfect cosmic speed trap, truly exists, and we have named it a black hole. A black hole is far more than an object of immense gravity. It is a segment of space where the gravitational pull has grown so powerful that it warps the very fabric of reality. Even light, the fastest entity known, cannot break free from its clutch, and if light is trapped, then nothing else has a hope of escaping. This is precisely why the border of a black hole is known as the event horizon. It is not a tangible barrier or wall, but rather a point of no return. Once anything crosses this invisible demarcation, it disappears from the rest of the universe. Not because it's been destroyed, but because all signals it could possibly generate are captured forever. But the most incredible detail is the mechanism of this trap. It is not some cosmic beast grabbing light and yanking it back. The phenomenon is rooted in the fundamental structure of space-time itself. Around a black hole, space is so profoundly distorted that all paths which once led away now exclusively point inward. It is like running up an escalator that is moving downward at an ever-increasing velocity. No matter how furiously you try to climb, you are inexorably carried down. In the vicinity of a black hole, you don't merely slide. You find that moving in any direction away from its center is literally impossible. If you were to fall into a black hole, and could somehow remain intact, you would notice nothing out of the ordinary as you crossed the event horizon. No sudden jolt or pull. To me, however, watching from a distance, your image would appear to freeze at the edge of that abyss, slowly reddening and dimming under gravity's influence, until it faded completely into infinity. Because it isn't just speed that is distorted here, but time itself. This is what sets this cosmic prison apart. It functions not through friction or physical resistance, but through pure geometry. The very shape of the universe is altered, making escape geometrically impossible rather than just physically difficult. You are not halted. Instead, every possible direction simply leads inward. Here, the speed of light is transformed from a mere limit into a definitive gatekeeper, separating what is inside from what is outside, and what is silenced from what can still send a message. This is what sets this cosmic prison apart. It functions not through friction or physical resistance, but through pure geometry. The very shape of the universe is altered, making escape geometrically impossible rather than just physically difficult. You are not halted. Instead, every possible direction simply leads inward. Here, the speed of light is transformed from a mere limit into a definitive gatekeeper, separating what is inside from what is outside, and what is silenced from what can still send a message. This is what sets this cosmic prison apart. It functions not through friction or physical resistance, but through pure geometry. The very shape of the universe is altered, making escape geometrically impossible rather than just physically difficult. You are not halted. Instead, every possible direction simply leads inward. Here, the speed of light is transformed from a mere limit into a definitive gatekeeper, separating what is inside from what is outside, and what is silenced from what can still send a message. Black holes are simply the most striking instances of such traps, as the universe contains other, more subtle boundaries where the speed of light dictates the limits of our knowledge. You can consider, for example, the boundary of the observable universe. For approximately 13.8 billion years, light has been journeying toward us since the dawn of time, and in that period, it has only managed to traverse a finite distance. Because of the continuous expansion of space, the most remote light we can presently see originates from a region that is now about 46 billion light-years from us. Anything existing beyond that frontier is currently invisible to you and me, not because something is obscuring it, but because its light simply hasn't had enough time to complete the immense journey to reach our eyes. Because of the universe's accelerating expansion, some information may be lost to us forever. You should consider that entire galaxies, complete with stars, planets, and perhaps even life, might exist beyond the edge of our observable cosmos. We are destined to remain ignorant of their existence, as they lie permanently beyond a boundary that light, our only connecting thread, can no longer cross. This isn't a trap of our making, but a fundamental cosmic constraint that defines the limits of what we can perceive and what can influence us. This cosmic speed trap is less a specific location and more a universal principle that appears wherever conditions like gravity or spatial expansion prevent light from transmitting information. The consequences of this are profound, though subtle. It means that our universe holds regions that are absolutely inaccessible, not due to technological limitations, but because any signal from us could never bridge the distance. An inviolable boundary exists in our reality, a kind of ultimate speed limit that functions not as a punishment or an artificial barrier, but as an intrinsic law woven into the fabric of existence itself. We can study this boundary, approaching it ever closer in our calculations and experiments, but it is a line that we are apparently not meant to cross. But what if, on the other side of this barrier, a realm governed by different principles contains particles for which our maximum speed is actually their minimum? On paper, such particles are theoretically possible, even though we have never observed them directly or found any traces of their existence or decay. Mathematics, however, allows for their reality. These hypothetical particles are called tachyons, a name that comes from the Greek word tachys, meaning fast, an entirely justified description. If tachyons truly exist, they don't simply travel at incredible speeds. Their very nature is to always move faster than light. This quality is not the result of some loophole in the laws of physics or a distortion in space-time, but is instead their natural, innate state. They can never slow down to the speed of light, because for them, that threshold is just as insurmountable as it is for us. In effect, they would inhabit a completely different mirror world of velocities. This is what makes them so incredibly strange. You can recall how our own reality is structured. Any object with mass is forbidden from reaching the speed of light. The more energy we pour into it, the closer it gets to that coveted limit, but its mass also increases at the same time. Ultimately, an infinite amount of energy would be needed to surpass this barrier, which makes the task impossible. Light, which is composed of photons, is a different matter entirely. Since photons possess no rest mass, they have no need to accelerate. Moving at the speed of light is their only possible state. It is their very nature. Now, let's return to tachyons. If they were real, their mass wouldn't just be zero or very small. It would have to be an imaginary number. In this context, imaginary is a specific mathematical term that relates to the square root of a negative number, like -1. While imaginary numbers are a very useful tool for calculations in most areas of science, especially in quantum mechanics, They rarely describe something that you can physically touch or measure in the real world. This makes tachyons doubly phantoms. They appear as solutions in our equations, but manage to elude any and all experimental confirmation. We are able to describe them, but we are completely unable to detect them. What makes their concept even more difficult for us to grasp is that they cannot be slowed down. You could never make a tachyon stop or even approach the speed of light from above, just as we cannot reach it from below. This establishes a remarkable mirror world where the same laws seem to apply, but in reverse. For instance, if you were to add energy to a tachyon, it would not accelerate. It would slow down, moving closer to the light barrier. As this happens, its mass would actually decrease, but it would still be unable to cross that boundary, just as we are. This naturally brings up a logical question. If tachyons cannot interact with our world in any way, why are they even necessary in our theories? In some versions of quantum field theory, the appearance of a tachyon is not a prediction of a new particle, but instead a kind of diagnostic signal, a mathematical hint that something is wrong with the theory itself, or that the system it describes is unstable. Once physicists correct this instability in the equation, the tachyon simply disappears from it. In other words, it was never a real particle at all, but served only as a mathematical red flag that signaled an error, not a new discovery. And yet, some scientists continue to wonder, what if they are real after all? What if, somewhere in the vast emptiness of space, there are entities moving so fast that we are fundamentally incapable of ever seeing them? They would outpace any signal they could possibly send, and could pass through matter without interacting, not because they are hiding, but because their sheer speed makes them elusive to our methods of detection. Answering this question is incredibly difficult. Our detectors all operate on the principle of interaction. A particle must reflect something, absorb something, or leave some kind of trace. If tachyons exist, they could theoretically pass through entire planets and stars without leaving the slightest hint of their presence. Perhaps, however, they might still leave behind indirect clues, some sort of interference in space, anomalies, or effects without visible causes, like a ghostly signature left by something whose appearance we missed. Physicists have searched for such traces by analyzing collider data for unexplained deviations in particle decay rates, but so far they have found nothing conclusive, only hypotheses. And here we confront the biggest problem of all, causality. The fact is, if something moves faster than light, then according to the special theory of relativity, it is capable of sending signals into the past, not from its own perspective, but from ours. The mathematics demonstrates that it is possible to model a situation where a tachyon arrives at its destination before it has even departed from its initial point, shattering our understanding of cause and effect. This isn't a matter of magic. It's a direct outcome of the equations themselves. If an object's velocity surpasses the speed of light, the very fabric of time for certain observers would warp so dramatically that the order of events could flip. At that point, you're not just dealing with exceptionally fast particles, but with the possibility of temporal paradoxes. Could an effect actually happen before its cause? Is it possible for you to read the reply to an email you haven't even composed yet? Most physicists approach this subject with immense caution, correctly pointing out that just because something is mathematically possible doesn't guarantee its existence in nature. A theory can produce numerous solutions that are never actually manifested in the real world. For this reason, tachyons continue to occupy the realm of fascinating yet highly improbable ideas. While their existence hasn't been disproven, it also remains entirely unconfirmed, forcing us to probe the very limits of our comprehension and ask if the speed of light is truly the ultimate cosmic speed limit. Yet, tachyons are not the only phantoms lurking at the frontiers of contemporary physics. Take virtual particles, for instance. They continuously flicker into existence from the vacuum, borrowing energy for an infinitesimal moment before they disappear. You can't observe them directly, but their impact is undeniably real, as they are the mechanism that explains the operation of fundamental forces. Then there's dark matter, an invisible substance that doesn't emit or reflect any light, which you cannot touch. Yet its gravitational pull on stars and galaxies is plain to see, holding everything together while staying completely hidden. Viewed in this light, tachyons serve less as a concrete prediction and more as a crucial signpost at the very edge of what we know. They might be unreal, but they raise a question to which we currently lack an answer, compelling us to wonder if there is something fundamental about the nature of speed itself that we are missing. This thought brings us to another phenomenon that appears to violate every conceivable boundary, a physical reality where distance seems to become entirely meaningless, and two particles act as a unified whole no matter how vast the space between them. This connection isn't conveyed through any wire or beam of light. It doesn't travel, but simply is, a phenomenon known as quantum entanglement. When two particles become entangled, they are bound by a shared state. If you measure a property of one particle, such as its spin, you will instantly know the corresponding spin of its partner, even if that particle is on the far side of the galaxy. This is not a signal or a transfer of information in any conventional sense, but a correlation that holds true, regardless of the separation. It certainly appears to be a direct defiance of the principle that nothing can exert influence faster than light. So what's truly going on? Entangled particles are not merely two connected objects. They are described by a single, unified mathematical function, making it impossible for you to completely describe one without also describing the other. This doesn't make them identical, but rather perfectly correlated. If one's spin is up, the other's will invariably be down. These states, however, aren't fixed ahead of time but exist in a superposition of all potential outcomes until the very instant you perform a measurement. As soon as you measure the first particle, its state becomes definite, and at that exact same moment, the state of the second particle is also determined, with no delay. This isn't because the first sent a message to the second, but because they are both components of a single, unfolding quantum event. Albert Einstein found this concept profoundly unsettling, famously calling it spooky action at a distance. To his orderly mind, the notion that a measurement here could instantaneously affect something over there seemed completely absurd, leading him to believe there had to be hidden variables or pre-written instructions ensuring the results were coordinated. However, both time and extensive experiments have shown his intuition to be incorrect. Beginning with the work of John Bell in 1960, physicists have demonstrated that no hidden variable theory can account for the correlations that are consistently observed. The connection between the particles is fundamentally non-local and quantum in nature. As counterintuitive as it might seem, this bizarre phenomenon operates within strict limits, as quantum entanglement, for all its apparent magic, does not allow you to break the universe's fundamental laws by transmitting information faster than light. It's impossible to use this connection to send a coherent message from one location to another. To understand why, imagine you and a friend have a pair of entangled particles, one on Earth and the other on Mars. When you measure a property of your particle, you instantly know the corresponding property of the one on Mars, because their states are always linked. The critical detail, however, is that the outcome of your measurement is entirely random. You cannot compel your particle to adopt a specific value to encode a signal. You can only passively observe whichever result emerges. Think of it as having a pair of enchanted dice. Whenever you roll a 3, you know with absolute certainty that your friend, light years away, has just rolled a 4, because their sum is always 7. But you have no ability to force your die to land on a 3. This inherent randomness serves as a cosmic safeguard, protecting the principle of causality and preventing any temporal paradoxes or messages sent to the past. What you are witnessing is not a signal being transmitted, but a profound, non-local link between objects that were once part of a unified whole. Nevertheless, the very concept of instantaneous action at a distance gives even the most pragmatic scientists reason to pause and think. All of physics as we understand it is founded upon interactions that spread from one point to another at finite speeds. Every influence, be it gravity or light, must travel through space. Even light itself, our benchmark for speed, requires time to cross a room or journey from the sun to us. Yet quantum entanglement seems to require no time at all. This mysterious bond doesn't rely on any mediator to communicate its state, nor does it diminish with distance. You could separate entangled particles by kilometers, by light years, or even place them at opposite ends of the universe, and their strange correlation would remain perfectly intact. This is not motion as you typically conceive of it. It is something else entirely, a phenomenon that challenges our deepest assumptions about space, time, and reality itself. For some physicists, this suggests that space itself, which you perceive as the stable stage for all existence, might be an illusion, or at least less fundamental than we assume. What if reality is built not on distance, but on relationships? Imagine if quantum entanglement isn't about particles traversing a void, but rather about observing separate aspects of a single, unified system. Under that interpretation, the very concept of speed becomes meaningless, because nothing is actually traveling anywhere. There is no voyage across space, only an intrinsic, pre-existing harmony. Consider our pair of coins, which are guaranteed to land on opposite faces. You feel their instantaneous connection only because it was imprinted upon them at the moment of their creation, making it an inherent property, not a signal you are detecting. Of course, the quantum realm is vastly more intricate, and any simple analogy like this one is bound to be incomplete. Yet it helps you to shift your entire perspective. It's possible that not all connections in the universe depend on movement. Some might be woven directly into the essence of being. These connections aren't physical tethers, but are instead shared conditions of origin, defined not by speed, but by symmetry. A symmetry that could permeate reality far more profoundly than you can yet comprehend. Certain researchers take this idea a step further, proposing that entanglement is more than just a peculiar feature of quantum mechanics. They speculate that it might be the very bedrock of space-time itself. What if the geometry of our cosmos, the entire tapestry of reality, emerged from an elaborate web of entangled quantum states. If this hypothesis proves true, entanglement ceases to be a bizarre exception to the rules of space and is revealed as their genuine source. While this remains a bold assertion on the frontiers of science, it aligns with a long-held human intuition. The ultimate universal constant might not be speed, but connection. This concept is incredibly challenging for you to grasp, as your entire life experience is founded on objects moving from point A to point B. Entanglement, however, demands that your imagination envision a form of instantaneousness that involves no travel, a proximity defined by a shared history rather than physical distance. In this framework, the expression faster than light loses all its meaning, as it presupposes motion, a trajectory, a start, and a finish. Entanglement possesses no pathway, no signal, and no go-between. It simply exists as a fundamental state. This realization offers you a glimpse beyond the familiar world, hinting that not all cosmic interactions require a bridge to connect them. However, while entanglement circumvents the notion of speed, there is another genuine process in the universe that seems to directly surpass the speed of light. You are accustomed to picturing space as a static backdrop, a silent, dark stage for the cosmic drama of stars and galaxies. This view is fundamentally mistaken, because space itself is dynamic and constantly expanding. And this expansion is happening faster than the speed of light. This doesn't imply that individual galaxies are hurtling through space at superluminal velocities in violation of physical laws. Instead, it signifies that the very fabric of space between them is stretching so rapidly that the distance grows faster than light can traverse it. This phenomenon is not a loophole in the laws of physics, but a direct outcome of them, permitted and even anticipated by Einstein's general theory of relativity. To understand this, picture two dots drawn on a deflated balloon. As you inflate it, the dots separate, not because they are crawling over the rubber's surface, but because the rubber itself is stretching between them. The same principle applies to galaxies. The fundamental cosmic rule, which dictates that nothing can travel through space faster than light, remains unbroken. But because space itself is not an object in space, that limit does not constrain its expansion. When you gaze into the depths of the cosmos, you are simultaneously looking back in time. As the farther an object is, the more time its light has taken to reach you. Beyond a certain threshold, however, that light will never get to you. This isn't a matter of patience. It's because the expanding universe is carrying its source away from you faster than light can travel toward you, meaning the fastest messenger in the cosmos ultimately loses this race. This invisible border is known as the cosmological horizon, and everything beyond it is receding from us at a velocity greater than that of light. In practical terms, this means there are entire galaxies you will never be able to see. Although their light departed billions of years ago, the ocean of space between you and it has since expanded so immensely that the message will never reach your cosmic shore, doomed to drift eternally without ever arriving. With each passing day, the count of these inaccessible galaxies increases. Even the galaxies you can currently observe at the very edge of your vision will eventually fade away. They won't burn out or fly off, but the expanding cosmos will stretch their light so profoundly that it will become invisible to any detector. If the present accelerated expansion persists, a time will arrive when only your own galaxy and a few close neighbors will remain visible from Earth. Everything else will lie beyond the light horizon, hidden from view. To a hypothetical observer in that distant and solitary future, the universe will look empty, confined, and deeply lonely. They would live their entire existence looking out from a tiny window, never knowing that beyond their sight lies an infinite expanse of galaxies, concealed from them forever by the expanding fabric of reality itself. In cosmology, you encounter an idea that seems to challenge not only common sense, but also the foundational principles of physics, the universe expanding faster than the speed of light. This isn't about some cosmic race. It's about something far more profound, a fundamental boundary on what we can ever know. This concept establishes the absolute edge of our observable reality, a limit defined not by a physical wall, but by the very structure of time itself. What's truly remarkable is that this boundary will always be there, no matter how advanced our spacecraft or powerful our telescopes become. It might feel like this realization strips away our hope, but I believe it is precisely this that lends cosmology its profound appeal. From just beyond this constantly shrinking horizon, light continues its journey to us. And this isn't just any light. These are ancient messengers from the distant past. You are seeing photons that have been traveling across the cosmos for billions of years. And all the while, the very space they traversed was stretching out beneath them, causing their energy to diminish over their immense voyage. When these photons finally strike our detectors, they deliver the earliest possible image of the nascent universe. We refer to this light as the cosmic microwave background, or relic radiation, and it represents the most pristine window into the past available to us. It is simultaneously the oldest phenomenon you can observe, and one of the most data-rich. This gives rise to an incredible paradox. Even as the expansion of space outpaces light, light itself finds a way to outpace time, preserving an invaluable signal for us across the eons. This journey gives a photon just enough time to deliver its message before being swept away, and this fleeting glimpse reveals another critical detail. The expansion itself is not a steady process. Its rate is constantly in flux, shaped by gravity, regular matter, and, most significantly, by dark energy. That enigmatic force acts like an unseen conductor, compelling everything to accelerate away from everything else. In the current epoch of the universe, dark energy is the dominant influence, which means the expansion is not merely continuing, it is speeding up. As a consequence of this acceleration, the process of objects receding from us at superluminal speeds is only getting more intense, which means our cosmic horizon is actively contracting. The window through which you can view the distant cosmos is slowly but irreversibly closing, and more of the universe is being rendered permanently inaccessible to us. Let me be clear. This doesn't imply some cataclysmic explosion is ripping galaxies apart in the distant void. It signifies that the very metric of space, the fundamental measure of distance itself, is undergoing continuous inflation. This stretching of space-time creates the illusion that the universe operates under incredibly rigid laws, not about the velocity of objects, but about the very path they travel on. Think of an ant on the surface of a balloon you're inflating, rather than a car speeding down a highway. The ant can remain perfectly still, but as the balloon expands, the distance between it and any other spot on the surface grows. If you inflate it fast enough, the ant will move away from another point faster than its own legs can carry it. This is precisely what is happening with distant galaxies. They aren't actively speeding away from us. They are being carried along by the expanding fabric of space-time. It's a silent, entirely imperceptible motion that you only become aware of as the voices from those distant worlds fade into an eternal quiet. Their signals simply stop arriving. With each passing year, this cosmic silence deepens, confirming that the fastest movement in the universe might not be a particle or a beam of light, but space itself, carrying entire worlds beyond the reach of our knowledge. However, if space is malleable enough to stretch, it's conceivable that it can do more. Perhaps it can also bend. And if it can be bent, maybe it can even be folded. This is the central idea underpinning theories about wormholes. These aren't just pathways through space. They are envisioned as true bridges connecting its most distant regions, offering the shortest possible route. This isn't achieved by something moving faster than light, but by radically shrinking the distance that needs to be covered. Imagine you take a sheet of paper and mark 2 points on opposite ends. The conventional path between them is a straight line across the paper's surface. But now, picture folding that sheet so the 2 points touch each other. The path effectively vanishes. You have transitioned from one point to the other instantaneously, not through speed, but through a manipulation of the geometry itself. This serves as a simplified model for a wormhole, a theoretical passage that links 2 entirely different areas of space-time. This isn't a tunnel bored through a planet. It's a proposed bridge through reality itself. A wormhole could theoretically connect 2 faraway stars within our own galaxy. Or, if certain mathematical models prove correct, it might even link 2 completely different universes, timelines, or dimensions. The truth is, we have no way of knowing for sure, as we've never observed anything of the sort. Yet, the very equations that describe gravity, Einstein's general theory of relativity, do permit this possibility to exist. In fact, one of the first exact solutions to Einstein's equations, discovered as early as 1916, detailed a structure remarkably similar to a wormhole, which was later named the Einstein-Rosen bridge. Initially, it was dismissed as little more than a mathematical curiosity, an odd artifact in the calculations. It was only later that physicists grasped that this structure could, in theory, create a hidden corridor of warped space connecting 2 black holes, forming a kind of portal. The very notion of wormholes, these hypothetical tunnels through the fabric of space-time, is undeniably captivating. However, as is often the case in science, a fundamental problem lurks behind the elegant concept. Actually, there are several of them. The primary challenge is their profound instability. If you can, try to imagine crossing a bridge constructed entirely from soap bubbles. That gives you a sense of the fragile nature of most theoretical wormholes. Even if such tunnels could form, their lifespan would be unimaginably brief, collapsing in less time than a photon of light could travel from one opening to the other. This isn't a simple closure. The entire structure doesn't just shut down. It is utterly annihilated, vanishing from existence itself. Its life cycle is a fleeting sequence of appearing, contracting, and disappearing in an infinitesimal moment. To hold such a cosmic passage open, you would require something that defies all currently understood physics. Stabilizing a wormhole would necessitate the use of a hypothetical exotic substance, which is often described as matter possessing negative energy. Its characteristics would need to be the complete opposite of everything familiar to us in the universe. This material wouldn't be subject to gravity's pull. Instead, it would actively oppose it, repelling rather than attracting. To keep the tunnel stable, such a substance would have to exert an outward push from within its walls, counteracting spacetime's natural tendency to collapse under its own tremendous mass. In the realm of classical physics that governs our everyday world, nothing remotely like this is known to exist. However, a small hint emerges from the most perplexing and mysterious field of science: quantum theory. It reveals that even in the perfect vacuum of empty space, pairs of virtual particles are constantly materializing and ceasing to exist. Within these transient quantum fluctuations, it's possible for incredibly brief bursts of this very negative energy to occur. Of course, these quantum effects are so minuscule and short-lived that they couldn't stabilize something as small as a grain of dust, let alone an entire cosmic tunnel. Nevertheless, they give us pause for thought, suggesting that the fundamental laws of the universe might be far more intricate than we currently perceive. This naturally leads to a profound question. What if humanity could one day learn to harness or amplify these quantum phenomena? In theory, it is not ruled out as an impossibility. So, let's imagine for a moment that we manage this feat and create or discover a stable Einstein-Rosen bridge. How would this impact our conception of speed? The answer is, not at all. The universal speed limit of light would remain completely inviolate. The real trick lies in a different concept entirely. Picture yourself needing to cross a massive mountain. You could hike for hours on a winding path around it, or you could use a direct tunnel bored straight through the rock. Your actual walking speed wouldn't increase, yet you'd arrive at your destination many times faster, simply because your path was immeasurably shorter. A wormhole functions as precisely this type of cosmic shortcut. It doesn't make an object travel faster. It dramatically reduces the distance it needs to cover. For an observer you left behind on Earth, your disappearance from one point in the cosmos, a near-simultaneous reappearance in another, would look like pure magic, a clear violation of Einstein's principles. But you would understand that no laws were broken. You simply traversed a path unavailable to light, which has to take the long way around. And from here, we plunge into a vast ocean of speculation and unresolved questions. What could guarantee the long-term stability of such a passage? What would be the fate of a starship, let alone a human being, navigating such an extreme warping of geometry? Would it be ripped to shreds? How would anyone control the entrance and exit points? Would they be fixed, or would they drift through space like the disconnected ends of a hose? Could a wormhole be harnessed for instantaneous communication? And then there is the most mind-bending possibility of all. Could such a gateway open a path to traveling through time? According to the theory of relativity, time progresses more slowly for an object moving at high velocity. Now, imagine one end of the wormhole stays put on Earth, while the other is accelerated to nearly the speed of light. The clock at the moving end would advance more slowly, creating a temporal difference between the entrance and the exit. You could, in theory, step into one end of the tunnel and emerge from the other before your journey even began. While the mathematics supports this possibility, we possess no evidence that it could ever be achieved in reality. Even if opening a portal in our backyards remains firmly in the realm of fantasy, the conceptual value of this idea is enormous. It compels us to reconsider our most fundamental ideas of what distance is and what it means for 2 points to be close. The concept demonstrates that the universe's geometry can be influenced not just by its physical contents, but also by our evolving understanding. It serves as a reminder that the ultimate limitation might not be speed, but the very fabric of space itself. If you can alter the shape of the game board, you effectively change the rules of the game. This very principle, not of overpowering space but of reshaping it, is the foundation for another seemingly fantastical idea, the Alcubierre drive. This theoretical construct proposes a spacecraft encased within a bubble of distorted space-time. The ship itself doesn't move faster than light. Rather, space contracts in front of it and expands behind it, effectively carrying the vessel along like a surfer riding the crest of a wave. Once again, this remains pure theory, derived from equations but demanding types of energy and methods of control that are, for now, far beyond our reach and belong to science fiction. For countless ages, humanity has looked up at the boundless dark of the night sky, dreaming of voyages to faraway stars. Yet behind this romantic notion lies a challenge of immense proportions, one that requires not just technological leaps, but a profound grasp of survival and the growth of civilization far from its terrestrial origins. How can we possibly ensure the human race thrives within the confines of a generation ship that is traversing the empty void for centuries? And what unseen biological and societal hurdles await us on such a journey? To address these questions, scientists utilize Monte Carlo simulation methods, which apply statistical analysis to model and project genetic variation over many generations. By inputting various parameters, such as the size of the starting population, the rate of mutations, and different reproductive models, these simulations can offer critical insights into the long-term genetic health of an isolated group. Monte Carlo modeling is instrumental in calculating the minimum population size necessary to preserve genetic diversity and ward off the debilitating effects of inbreeding depression. You must also consider that any model has to account for random chance, like accidents or diseases, which could seriously affect the population. This makes such simulations absolutely essential for building a sustainable human colony that can flourish for centuries. To maintain genetic diversity, you need carefully planned reproductive strategies and potentially even genetic screening. Consequently, the crew has to understand the vital importance of their genetic health and the actions required to protect it, from monitoring gene diversity to making informed choices about partnerships and child-rearing. Research indicates that if you want to preserve genetic health across multiple generations, you need a starting population of at least 100 individuals. This number isn't arbitrary. It stems from the work of scientists like Frederick Marin and Camille Bellew, who have conducted comprehensive studies on the genetic dynamics within small, isolated groups. In their research, Marin and Bellew employed Monte Carlo simulations to investigate a wide range of potential outcomes, factoring in different population sizes and reproductive approaches. Their work clearly shows that with an even gender ratio and an ideal rate of reproduction, an initial group of 100 people can sustain a healthy gene pool. A population of this size is your safeguard, ensuring that problems like genetic drift and inbreeding don't compromise the health and viability of future generations. Furthermore, this initial population must grow to 500 within a few generations, a step that I believe is critical for creating a stable and resilient community capable of handling any unforeseen crises. Naturally, the design of a generation ship must accommodate this growing population, which means you need to plan for adequate living space, resources, and social frameworks. The vessel has to provide everything from educational and medical facilities to recreational areas, maintaining a careful balance between shared spaces for community activities and private quarters for personal life. Beyond just the physical infrastructure, however, you have to find ways to preserve social cohesion and cultural continuity. This means the crew must cultivate a shared identity and a common sense of purpose to build cooperation and resilience. In this, I see cultural and educational programs playing a fundamental part, as they are the very tools for transmitting the knowledge and values that are indispensable for the mission's ultimate success. Ultimately, effective planning for the crew and the population is the linchpin for the entire endeavor of a generation ship. By leveraging advanced genetic simulations and research, we can work to ensure that the population remains healthy and viable for the long haul. Through meticulous planning and a deep commitment to both social and genetic well-being, humanity can thrive on its journey to the stars. Above all, designing a vessel that can sustain human life for centuries requires you to build a self-contained environment that mirrors the essential functions of Earth, including generating artificial gravity, producing food, and recycling critical resources like water and air. One of the most critical design challenges you'll face is the creation of artificial gravity to preserve the crew's health and well-being. As you may know, prolonged exposure to microgravity results in severe health problems, including muscle atrophy and a significant loss of bone density. To counteract these effects, generation ships could employ rotating structures to generate a centrifugal force, which perfectly simulates the gravity we experience on Earth. The most practical approach I can envision is a massive rotating ring, or a cylindrical section where the crew lives and works. As this structure spins at a specific velocity, the centrifugal force pushes the inhabitants outward, mimicking the sensation of gravity. For example, a ring with a radius of 100 yards would need to rotate at approximately 3 revolutions per minute to create an artificial gravity equivalent to Earth's. A design like this not only supports physical health but also provides a familiar environment that can help mitigate the psychological strains of living in space. Equally vital for sustaining a population across generations are reliable and efficient food production systems. In this area, hydroponic and aeroponic technologies offer a solution for cultivating crops without soil, instead using nutrient-rich water or mist to feed the plants. These methods are extraordinarily efficient, consuming far less water and space than conventional agriculture, and are perfectly suited for the controlled environment of a starship. Hydroponic systems work by growing plants with their roots submerged in a nutrient solution, while aeroponic systems deliver those nutrients directly to the roots using a fine mist. Both of these systems allow you to cultivate a diverse range of crops, from leafy greens to root vegetables, ensuring a balanced diet for the crew. They can also be automated and precisely controlled to guarantee a stable and dependable food supply, which can be further improved through genetic modification and selective breeding to increase crop yield and nutritional value. Finally, an efficient method for recycling water and air is absolutely crucial for the sustainability of a generation ship. Water recycling systems must be capable of reclaiming and purifying all wastewater, ensuring a continuous supply of clean water for drinking, cooking, and crop irrigation. Advanced filtration and purification technologies, much like those used on the International Space Station, or ISS, have already demonstrated incredible levels of efficiency. For instance, the ISS water recovery system can recycle up to 98% of all wastewater, including urine and sweat, a level of efficiency you must achieve for any mission where resupply from Earth is simply not an option. The generation ships of the future must elevate this efficiency to an entirely new level, pursuing almost complete recycling to drastically reduce the reliance on vast water stores. The reclamation of breathable air is just as vital, demanding systems that can effectively filter out carbon dioxide while restoring oxygen levels. It is possible to combine natural solutions, like plant photosynthesis, with engineered carbon dioxide scrubbers to sustain a well-regulated atmosphere. In addition to producing oxygen, plants also enhance the crew's psychological state by providing a tangible link to the natural world. Experiments like the Biosphere 2 project have showcased the viability of crafting closed ecological systems in which plants, people, and microbes can coexist by recycling air, water, and vital nutrients. While Biosphere 2 encountered its share of difficulties, the project affirmed the practicality of these systems and taught us invaluable lessons that can be applied to the design of life support for generation ships. To realize a self-sufficient starship, it is essential to merge cutting-edge technology with natural systems, all to safeguard the health and morale of the inhabitants. The success of any mission spanning multiple generations hinges on more than just the ship's physical and technological capabilities. It is imperative to cater to the psychological, social, and educational requirements of the crew, thereby preserving their health, motivation, and unity over the course of the long journey. Prolonged isolation and confinement can have a severe negative effect on morale and mental wellness, just as a lack of new experiences and an extended disconnect from Earth can foster feelings of loneliness, depression, and deep-seated anxiety. Tackling these issues head-on is fundamental to keeping the crew stable and driven. To address mental health and maintain a cultural tether to home, virtual reality technology presents a very promising avenue by generating immersive simulations of Earth's environments. VR can offer a powerful feeling of escape and comfort, enabling crew members to experience forests, oceans, or even social events, which helps to counteract feelings of isolation. Artificial intelligence is also poised to play a crucial role in bolstering the crew's psychological fortitude. AI-driven therapists, exemplified by NASA's Simon 2.0, can provide personalized counseling, track emotional well-being, and recommend coping mechanisms for stress and interpersonal issues. The journey to the stars calls for more than just technological brilliance. It requires a deep-seated dedication to the human element. By thoughtfully addressing the crew's psychological, social, and educational needs, we can foster the resilience and solidarity of every generation that carries the torch of exploration. A foundation for a flourishing interstellar community will be built upon advanced technologies, such as virtual reality and artificial intelligence, working in concert with robust cultural and social frameworks. As you and I venture out of our solar system, this harmonious integration of humanism and innovation will be our guide to new worlds, cementing our destiny as an interstellar species. Within a cosmos teeming with unanswered questions, one query rises above all others. Are we truly alone? This puzzle, famously known as the Fermi Paradox, directly confronts our perception of the universe and our own significance within it. Named for the physicist Enrico Fermi, who first raised the issue during a casual lunch, the paradox presents us with a glaring contradiction. On one side, the staggering quantity of stars, akin to every grain of sand on Earth, points to a high probability of extraterrestrial civilizations. On the other, our skies are unnervingly quiet, offering no trace of them. Despite our sophisticated technologies and ever-increasing ability to probe space, not a single signal from the cosmic deep has ever reached our instruments. This profound silence brings up some fundamental questions. What obstacles could be preventing other civilizations from either making contact or crossing the stellar voids? Perhaps the immense distances or the inherently brief lifespan of civilizations could account for their apparent non-existence. Or maybe the solution is embedded in the very process of how life emerges and endures throughout the universe. Amidst the countless stars, our own solar system gives us clues about both the potential for and the constraints on life beyond Earth. Distant moons, encased in ice, conceal vast oceans beneath their frozen surfaces, which reflect the conditions thought to have spawned life on our own world. These hidden oceans, protected from the brutal environment of space, might very well be nurseries for intelligent life. However, it's highly probable that such creatures would be trapped within their icy domains, perhaps not even capable of imagining a reality beyond them. This recently suggested hypothesis forces us to re-examine the variables of the Fermi Paradox, and I want to explore with you exactly how it alters the search for an answer. The persistent silence from the cosmos is an enigma that has captivated thinkers for many years. You might picture a universe alive with technological wonders and interstellar chatter bridging the gaps between stars, an expectation fueled by our science fiction and logical frameworks like the Drake equation. This equation attempts to estimate the number of technologically advanced civilizations in our Milky Way galaxy. Yet, as our exploration of space deepens, the reality we find is starkly different, and the hoped-for galactic conversation has yet to begin. The Fermi Paradox asks a strikingly straightforward question that has baffled scientists and the public for generations. In a galaxy with billions of stars, many with planets like ours, where is everyone? A widely accepted concept is the Great Filter Theory, which posits that somewhere along the path from a planet's formation to a galaxy-colonizing civilization, there exists a monumentally improbable step that almost no species can successfully navigate. Alternatively, the zoo hypothesis speculates that highly evolved extraterrestrial beings deliberately conceal their presence from us, allowing for our natural biological and social development, much like zookeepers observing wildlife from a distance. It's quite perplexing that despite our advanced antennas and sophisticated listening arrays, we haven't intercepted even the faintest signal from the cosmos. This silence implies that our detection methods may be incompatible with alien communication technologies, or, more unsettlingly, that intelligent life is either incredibly scarce or fleeting due to cosmic calamities or self-annihilation. Considering the immense regions of space we have already surveyed, it becomes challenging to arrive at any other conclusion. This cosmic quiet could simply mean that our understanding is flawed, or that our search is being conducted in the wrong manner, or at an inopportune moment. However, it's possible the solution is far more straightforward than we imagine, and a compelling new idea to consider is the Aquarium Worlds hypothesis. For a long time, the quest for extraterrestrial life has centered on finding conditions similar to our own, worlds within the habitable zones of their stars, complete with liquid water and a life-sustaining atmosphere. This perspective, however, might be excessively restrictive, as it dismisses the possibility of life that doesn't fit our terrestrial model. The Aquarium Worlds hypothesis proposes a fundamental change in our search strategy, suggesting that life flourishes in subsurface oceans, completely sealed beneath thick ice shells. These environments provide remarkable stability, shielding any developing life from cosmic dangers like radiation and asteroid impacts, thereby allowing complex ecosystems to evolve in total seclusion. This theory takes inspiration from the work of researchers like Alan Stern, whose efforts in space exploration have illuminated the enigmas of icy bodies within our own solar system. For instance, The New Horizons mission unveiled fascinating characteristics on Pluto and its moon Charon that point to the existence of subsurface oceans, and similar conditions might even exist in the frigid depths of the Kuiper Belt. In our own celestial neighborhood, moons such as Enceladus orbiting Saturn and Europa around Jupiter display geysers that eject water vapor and ice, a phenomenon witnessed by instruments on the Cassini spacecraft, which signals dynamic, active worlds hidden beneath their frozen surfaces. This theory takes inspiration from the work of researchers like Alan Stern, whose efforts in space exploration have illuminated the enigmas of icy bodies within our own solar system. For instance, the New Horizons mission unveiled fascinating characteristics on Pluto and its moon Charon that point to the existence of subsurface oceans, and similar conditions might even exist in the frigid depths of the Kuiper Belt. In our own celestial neighborhood, moons such as Enceladus orbiting Saturn and Europa around Jupiter display geysers that eject water vapor and ice, a phenomenon witnessed by instruments on the Cassini spacecraft, which signals dynamic, active worlds hidden beneath their frozen surfaces. This theory takes inspiration from the work of researchers like Alan Stern, whose efforts in space exploration have illuminated the enigmas of icy bodies within our own solar system. For instance, the New Horizons mission unveiled fascinating characteristics on Pluto and its moon Charon that point to the existence of subsurface oceans, and similar conditions might even exist in the frigid depths of the Kuiper Belt. In our own celestial neighborhood, moons such as Enceladus orbiting Saturn and Europa around Jupiter display geysers that eject water vapor and ice, a phenomenon witnessed by instruments on the Cassini spacecraft, which signals dynamic, active worlds hidden beneath their frozen surfaces. But you might ask how these icy moons and dwarf planets connect to the Aquarium Worlds theory. The answer is found in the intricate balance of gravitational forces, radioactive decay, and possibly deep-sea hydrothermal vents, all of which could work together to sustain these hidden oceans. Within such environments, life as we understand it, or perhaps forms of life entirely new to us, could find a way to prosper, protected from the harsh vacuum of space by a formidable ice barrier. In these isolated ecosystems, life could reach great complexity without ever seeing the stars, or even conceiving of a universe beyond its icy ceiling. This possibility raises a profound question. How would such insulated beings ever communicate with the outside, or even develop a concept of a reality larger than their own? The idea is certainly baffling because it forces us to reconsider our assumptions about what an advanced civilization should look like. Following this line of thought, one could speculate that the universe is teeming with life, all of it concealed within these natural sanctuaries. It could be that our galaxy is filled with these silent, sequestered worlds, whose inhabitants are unknowingly sharing the cosmos right alongside us. Within the icy crusts of faraway worlds, the entire notion of communication would evolve along a completely different path from our own terrestrial experience. In these concealed oceans, life forms might pioneer distinct methods of interaction, shaped by their unique and isolated surroundings. Here on our own planet, the deep oceans provide a model for how life adapts to the perpetual darkness of subsurface realms. Marine animals like whales and dolphins use sound to communicate across vast distances, sometimes thousands of miles, a technique perfectly suited to the dense medium of water. This earthly parallel suggests that beings in the hidden oceans of frozen worlds could also depend on sound or other non-visual methods, rendering technologies like radio signals entirely unnecessary. In a world without light, these creatures might evolve sophisticated echolocation, enabling them to construct a picture of their world through sound waves. Knowledge acquisition in such a context would be fundamentally different, likely centered on interpreting subtle acoustic data rather than electromagnetic or visual signals. It is entirely plausible that these enigmatic beings, thriving in their insulated domains, possess an intricate understanding of their immediate environment while remaining completely oblivious to the cosmos that lies beyond. Yet, the vast universe, with its countless worlds, offers not just opportunities for life but also immense difficulties for any civilization that dreams of interstellar travel. The immense gravitational pull of a home planet stands as one of the most significant barriers to achieving that dream. This particular challenge introduces another vital component into the Drake equation, which is known as the exoplanetary escape factor, designed to evaluate how feasible space travel would be for civilizations on worlds different from ours. This factor serves as a crucial supplement to the Drake equation, giving us a quantitative way to assess the obstacles an alien civilization would need to overcome to break free from its planet's gravitational hold. The formula for a celestial body's escape velocity reveals that larger, more massive planets present an extraordinary hurdle. For context, Earth, with an escape velocity of 11.19 kilometers per second, provides a benchmark for this comparison. Consider for a moment a theoretical super-Earth, a world with a mass far exceeding our own. Its gravitational pull would create an escape velocity so high that it would render conventional spaceflight an impossible dream. You can just imagine the immense engineering and energy demands required for a launch from a planet so much larger and more massive than Earth, creating celestial prisons for any inhabitants. The escape velocity from these worlds would be drastically higher, necessitating propulsion technologies that are currently beyond our wildest imaginations. It's entirely possible that such planets teem with life, perhaps even advanced civilizations, yet they would be forever confined, their skies remaining an unreachable frontier. These societies might evolve without any awareness of the greater cosmos, their technological progress perpetually limited to their planet's surface. However, you might wonder if these civilizations could find other ways to reach for the stars. Perhaps innovations like space elevators, orbital rings, or even tapping into their planet's rotational energy could offer a solution to the overwhelming challenge of high escape velocities. But even these remarkable feats of engineering would demand material and energy resources on a scale that we can barely conceive of today. This same principle of isolation becomes even more pronounced when you think about life developing on icy moons and dwarf planets, which are sealed beneath thick shells of ice. While these environments offer protection and stability for life to emerge, they also impose profound layers of separation for any intelligent beings that might arise there. For them, the cosmos might not even be a concept, hidden away behind an impassable barrier of ice and rock. It forces you to ask how such beings would comprehend their position in the universe, and what extraordinary efforts they would need to undertake just to break through their icy ceiling into the unknown. It stands to reason that on a world bound by immense gravity or a dense outer shell, the rhythm of life and the course of civilization would follow a very different trajectory. The focus of any intelligent life would likely be directed inward, toward understanding and mastering their own world. Under such environmental constraints, these societies would probably concentrate on perfecting their immediate surroundings, optimizing their habitats, and conducting deep explorations of their own planet. It would be no surprise, then, if they never communicated with the outside universe, because the very notion of space travel would require leaving their home, an idea that is profoundly alien in every sense of the word. As we now approach a new chapter in space exploration, our attention is shifting not just to distant stars, but also to the frozen sentinels within our own solar system. In the coming years, a number of ambitious missions are scheduled to explore these icy domains. The Europa Clipper mission, set to launch in October of this year, is headed for Jupiter's moon Europa, while Dragonfly is slated for a 2028 launch to Titan, and several conceptual missions are being proposed for Saturn's moon Enceladus. These celestial bodies, which you might have once dismissed as frozen wastelands, are now viewed as the most promising locations to search for extraterrestrial life in our solar system. These missions are equipped with sophisticated technologies designed to pierce the icy crusts and investigate the vast oceans thought to lie beneath. By studying the composition of water plumes ejected into space and analyzing ice geology, scientists are hoping to uncover signs of life, or at least the necessary conditions for it to exist. Although we currently have no direct proof of alien life in our system, this is likely to change within the next decade, offering new clarity on the question. The data we gather could provide strong support for the theory that life can thrive in conditions radically different from those on Earth, suggesting the universe is filled with hidden life in these isolated aquarium-like worlds. Conversely, if our search yields nothing, we may have to set this idea aside and look for answers elsewhere. But I believe one thing is certain. Our quest, whether it uncovers vibrant alien ecosystems or just desolate voids, will permanently reshape our cosmic perspective and push us forward into the next great age of human discovery. Saturn itself has long captured our collective imagination, from ancient cultures to present-day astronomers. Intriguingly, the Maori people of New Zealand, despite being separated by oceans and without telescopes, were somehow aware that Saturn possessed rings, a fact that only adds to its mystique. Saturn has consistently represented the unknown and the enigmatic, with its famous rings being a source of fascination since Galileo's time. But what if I told you that these rings, which seem so permanent, are actually a temporary cosmic feature? The planet's allure is further magnified by a storm twice the width of Earth, a baffling hexagonal formation that rages at its north pole. You have to wonder what forces could conspire to create such a perfectly geometric structure. The mysteries don't stop there, as Saturn's moons, Titan and Enceladus, present conditions that could conceivably harbor life. With their lakes of liquid methane and geysers that spray water and organic compounds into space, these moons are more than just celestial objects. They are potential abodes for living organisms. Let's delve deeper into this puzzling giant and its cosmic secrets. Our exploration starts with Galileo, the Italian astronomer who, in 1610, first aimed his telescope at Saturn. He was perplexed by what he observed, describing the planet as having what looked like ears. He couldn't have known he was seeing the edges of Saturn's spectacular rings, a feature that would continue to confound astronomers for many years to come. By today's technological standards, Galileo's telescope was quite crude, so the real nature of Saturn's strange appendages remained an unsolved puzzle. It wasn't until 1655 that Christian Huygens, using a much-improved telescope, was able to correctly identify them as a system of rings encircling the planet. As we jump forward into the modern era, you see the Pioneer 11 mission become the first spacecraft to perform a flyby of Saturn, which it did in 1979. The very first close-up pictures of Saturn and its ring system came from this mission, which revealed complex structures previously invisible to telescopes on Earth. However, the Cassini spacecraft was what truly unveiled the planet in its full splendor. Following its launch in 1997, Cassini reached Saturn in 2004 and dedicated 13 years to investigating the planet, its moons, and its rings. From identifying plumes of water ice on Enceladus to capturing the strange beauty of the hexagonal storm at the North Pole, Cassini completely transformed our knowledge of this far-off world. Here's a fascinating detail for you to consider. Long before any telescopes were invented, the Maori people of New Zealand held myths that depicted Saturn with a parara, which translates to a belt encircling it. The question of how they could have known this is still a topic of intense debate and speculation. Yet, as we'll explore further, this is just one of the many enigmas that Saturn presents. I want you to think about what could possibly form a hexagonal storm that is wider than our entire planet. Saturn's North Pole is home to a geometric puzzle, a six-sided storm that has baffled scientists for decades. This hexagonal marvel isn't merely a feature on the surface. It represents a profound and lasting enigma that pushes the limits of our comprehension of fluid dynamics and planetary atmospheres. The hexagon was initially spotted back in 1981 by the Voyager spacecraft. It was the Cassini mission, however, orbiting Saturn from 2004 until 2017, that provided us with an unparalleled view of this cosmic phenomenon. High-resolution photography from Cassini showed a symmetrical, orderly flow that encircled a hurricane-like vortex in the hexagon's core, presenting a picture of geometric precision that stands in stark contrast to the turbulent weather systems found on Earth. So, what is the driving force behind this hexagonal storm? A team of researchers from Harvard University proposed a three-dimensional model which theorizes that deep thermal convection within Saturn's outer layers could be responsible. This model suggests the storm might plunge thousands of kilometers into Saturn's atmosphere, far deeper than we are able to observe. Remarkably, scientists have successfully recreated this hexagonal shape under laboratory conditions, and while these experiments can't fully replicate Saturn's intricate atmosphere, they do provide valuable insights into such alien phenomena. Saturn's hexagonal vortex is dramatically different from Earth's polar vortex, which is known for being irregular and much less stable. This disparity brings up fundamental questions about the properties that separate the atmospheres of gas giants from those of terrestrial planets like our own. The sheer longevity of the hexagon is yet another puzzle. It has been continuously observed for at least 40 years, and likely for much longer, suggesting that its power source is a stable and maybe even permanent feature of Saturn's internal mechanics. Now, let's turn our attention from the perplexing hexagon to another of Saturn's marvels, its rings. These are not simply celestial decorations, but are in fact dynamic, constantly evolving systems that continue to captivate both astronomers and the public. But I ask you, what are these rings actually composed of, and what makes them so surprisingly temporary? Saturn's rings are made up almost entirely of water ice, with small amounts of rocky material and dust mixed in. The particles within them vary in size from microscopic specks to enormous chunks as large as a house. These icy fragments are in constant orbital motion, shaped by the immense gravity of Saturn and the subtle gravitational influences of its many moons. The ring system is organized into several distinct subdivisions separated by gaps, with the most famous being the A, B, and C rings, which are divided by features like the Cassini division, a 3,000-mile-wide gap separating the A and B rings. There has been a long-standing debate about the origin of Saturn's rings. One prevailing theory proposes they are the debris from a moon that was shattered long ago. Another suggests they consist of primordial material from the formation of the solar system that was captured by Saturn's gravitational pull. More recent analyses, based on the rate of dust accumulation, indicate the rings could be significantly younger than Saturn itself, perhaps only around 400 million years old. Contrary to how they might appear, Saturn's rings are not permanent fixtures. They are gradually vanishing because of a process called ring rain, which involves ring particles being pulled down into Saturn's atmosphere. This phenomenon is sped up by the constant bombardment of micrometeoroids and by interactions with the planet's magnetic field. Based on the current rate of decay, some scientists forecast that Saturn's rings could completely disappear within the next 100 million years. The loss of the rings won't just change how Saturn looks. It could also significantly affect its atmosphere and magnetic field. It's a moment where you can reflect on how even the most breathtaking features in our universe are subject to the unyielding laws of physics, eventually destined to become a part of cosmic history. Saturn, the iconic ringed giant of our solar system, is more than just a visual spectacle. It's also a cosmic arena that is home to some of the most fascinating moons you can imagine. Two of these moons, Titan and Enceladus, have thoroughly enchanted scientists and ignited discussions about the possibility of life existing beyond our world. Titan, which is Saturn's biggest moon, remains as a world cloaked in mystery, with a thick atmosphere brimming with organic compounds and a surface that hosts lakes and rivers of liquid methane. What is truly stunning, however, is the speed at which Titan is moving away from Saturn. It is drifting at a rate 100 times faster than formerly believed, a remarkable 4.3 inches each year. This accelerated departure points to a dynamic and evolving relationship between the moon and its parent planet. Could this rapid drift be affecting Titan's internal processes and, by extension, its potential to support life? The moon's atmosphere, dense with organic compounds like nitrogen and methane, combined with the prospect of a subsurface ocean, makes it an exceptionally compelling target in the hunt for extraterrestrial biology. It leads you to wonder what life might actually be like in a setting so drastically different from our own. And we shouldn't overlook Enceladus, another of Saturn's moons, which presents a completely different yet equally intriguing world. This icy body boasts a remarkably reflective surface, making it the most brilliant object in the solar system. Enceladus elevates the very definition of an ocean world. It not only harbors a subterranean sea, but also propels the contents of this ocean into space, creating a plume that can be directly sampled by our spacecraft. The ocean itself holds nearly all the chemical components required for life, which includes heated, mineral-laden water emerging from hydrothermal vents. Such vents could create the exact environment needed for life as we understand it. Here on Earth, these features are swarming with organisms adapted to harsh environments. Which makes you wonder, could similar yet alien life forms be thriving around the vents on Enceladus? Furthermore, Enceladus is responsible for feeding Saturn's E-ring, a distinctive characteristic that deepens the intricate connection between the moon and its parent planet. These frozen particles ejected into the ring provide a direct glimpse into the moon's internal composition, holding clues that might reveal its deepest secrets. It's fascinating how Titan and Enceladus, two moons of the same planet with starkly different natures. Both offer powerful arguments for the possibility of life, continuously stoking our scientific curiosity. As you consider the chances for life on Saturn's moons, it's important to realize our exploration extends beyond telescopes and simulations. Future missions are being designed to investigate these worlds directly, hopefully providing answers to our most urgent questions. Let me introduce you to Dragonfly, NASA's bold mission to Titan, planned for a launch in the 2030s, which has a singular primary goal: to find the fundamental components of life. This advanced rotorcraft is designed to traverse Titan's varied terrain, from its expansive dunes to its ancient impact craters. It will be tasked with analyzing the intricate organic molecules found in Titan's atmosphere and across its surface, yielding priceless information about the moon's chemical environment. Outfitted with a comprehensive array of scientific tools, Dragonfly's purpose is to decipher the geological forces at play on the moon and how they relate to its capacity for hosting an alternative recipe for life. Although there are no missions currently scheduled for Enceladus, its potential for harboring life has placed it at the top of the list for future exploration. Researchers have conceptualized missions that would navigate through the moon's cryovolcanic plumes to directly analyze its subterranean ocean for biosignatures or the precursors to life. The confirmation of hydrothermal vents within its ocean only deepens the mystery, pointing to an environment where life could plausibly flourish. In spite of the immense technical difficulties involved, a dedicated mission to Enceladus holds the potential to completely reshape our comprehension of life in the solar system. It could offer definitive proof of extraterrestrial organisms or, failing that, provide critical insights into the necessary conditions from which life can arise. As I touched on before, our previous belief that Saturn's rings were permanent was mistaken. New research indicates that a process unfolding over hundreds of millions of years is making these magnificent icy structures gradually disappear. According to findings from the Japan Aerospace Exploration Agency, this material, which is primarily water, is lowering the electron density in the planet's upper atmosphere, in a phenomenon known as ring rain. This effect has a substantial influence on the atmospheric conditions of Saturn. And you should understand, this isn't a mere drizzle. It's a deluge that funnels an amount of water comparable to an Olympic-sized swimming pool onto the planet every 30 minutes. The puzzle deepens when you consider the comparative newness of Saturn's rings. The planet itself is approximately 4.6 billion years old, yet data from NASA's Cassini spacecraft implies the rings could be as young as a few 100 million years. This discrepancy forces us to ask what kind of cataclysm could have formed them. Was it a moon that was torn apart? Or maybe a comet that was ensnared by Saturn's gravity? Cassini's cosmic dust analyzer introduced yet another piece to this puzzle. During its 13-year mission, it gathered 163 dust grains originating from outside the Saturnian system, which revealed the rings to be exceptionally clean, suggesting they simply haven't been around long enough to gather significant cosmic debris. This pristine state of the rings begs the question, if they are indeed young, why haven't they gathered more interplanetary dust? The scarcity of this material challenges our models of their age and how they interact with the wider solar system environment. You could almost imagine the rings existing within a cosmic cleanroom, somehow shielded from the dust that fills the space around them. As this depletion continues, the very appearance of Saturn is set for a radical transformation. The rings have long been the planet's defining characteristic, and their eventual absence could initiate a chain reaction, possibly modifying wind currents, the planet's albedo and heat retention, and even the behavior of its well-known massive storms, making the full scope of these changes a topic of profound scientific fascination. It's fascinating to consider that the destiny of Saturn's rings is likely interwoven with its moons. A leading hypothesis proposes that gravitational turmoil might have shattered one or more of Saturn's icy moons, supplying the raw material for the rings we see today. In essence, the rings and moons are engaged in a kind of cosmic dance, with each partner affecting the other. As our studies of these bodies progress, I am certain that the fate of one will help us unravel the secrets of the other. Humankind is now poised at the threshold of a new age, one that will be characterized not just by continued exploration, but by the audacious ambition of colonization. For many decades, our focus has been locked on two specific targets: our familiar celestial partner, the Moon, and the crimson point of light in our heavens, Mars. Worlds that were once confined to the realm of science fiction are now extending an invitation, promising us glimpses of new frontiers. Yet, moving past these more familiar destinations, you find a world veiled in enigma, one that fundamentally redefines what we consider a moon to be. I'm talking about Titan, the largest of Saturn's moons, a world shrouded in a dense atmosphere, an extraordinary feature for a satellite. It's a place where rivers and lakes are composed not of water, but of liquid methane and ethane, where the rain is akin to gasoline, and the cold is more extreme than anything you could imagine on Earth. Despite this alien environment, Titan holds the potential for something truly remarkable. Could this world, so fundamentally different from our own, be the very key to humanity's future among the stars? Is it possible that this far-off moon contains the secrets not only for our survival, but for flourishing well beyond the confines of our home world? When you look back through the annals of space exploration, the Moon and Mars stand out as prominent symbols of human aspiration. Our closest celestial companion, the Moon, has perpetually graced our night sky, representing our deep-seated urge to travel beyond Earth. Meanwhile, Mars, with its uncanny similarity to our planet, inspires our visions of establishing a new cosmic home. However, even with its proximity, the Moon poses considerable obstacles. Its surface is a desolate expanse, completely lacking an atmosphere and offering zero defense against the severe conditions of space. The lunar environment is a vacuum that subjects astronauts to radical temperature fluctuations and intense radiation. This absence of an atmosphere means there's no breathable air, no wind to transmit sound, and no atmospheric layer to buffer against the constant bombardment of solar and cosmic rays. Mars, while appearing more Earth-like, comes with its own set of formidable difficulties. Its tenuous atmosphere, consisting mainly of carbon dioxide, provides minimal shielding from solar and cosmic radiation. You'll find the Martian environment to be incredibly harsh and unforgiving, with polar temperatures plummeting to -143 degrees Fahrenheit. Furthermore, the lack of a global magnetic field leaves the surface completely vulnerable to the relentless force of the solar wind and cosmic rays. Titan, however, offers a profoundly different setting. Wrapped in a substantial atmosphere, Saturn's largest moon provides a natural shield against the hazards of cosmic radiation. This atmosphere, which contains more nitrogen than even Earth's, is the crucial element protecting future colonists from the radiation that relentlessly batters less shielded worlds like the Moon and Mars. Yet, Titan's atmosphere is more than just a protective layer. It's a portal to new possibilities. In contrast to the Moon and Mars, the atmospheric pressure on Titan's surface is 1.5 times that of Earth, presenting a surprisingly familiar pressure environment for human explorers. This dense atmosphere creates fresh pathways for exploration and settlement, opportunities that remain far beyond our grasp on more conventional celestial targets. As we reevaluate our ambitions for space colonization, Titan presents itself as a powerful alternative. It's a world where the very atmospheric and radiation problems that constrain our efforts on the Moon and Mars are transformed into its greatest assets. Titan encourages you to envision a future where humanity could thrive beneath the shelter of an alien sky. A future in which the enigmas of this remote moon serve as the foundation for our expansion across the cosmos. This moon of countless secrets, orbiting Saturn, was first identified in 1655 by the Dutch astronomer Christian Huygens, and it has since sparked the curiosity of scientists, artists, and visionaries.
Titan is a world that is simultaneously reminiscent of Earth and profoundly dissimilar. Its environment is unlike anything else you'll find in our solar system, as it's the only known moon with a significant atmosphere. It also ranks as the second largest moon in the solar system, surpassed only by Jupiter's moon, Ganymede. But its sheer size isn't what makes Titan so unique. Rather, it's the intricate composition of its atmosphere and surface that truly sets it apart. The moon is enveloped in a thick, nitrogen-dominant atmosphere, compositionally similar to Earth's, but substantially denser and more expansive, which is infused with organic molecules that produce a hazy orange glow, obscuring its surface from direct observation. This nitrogen-heavy atmosphere offers protection from solar radiation, a stark difference from the exposed environments of the Moon and Mars. Beneath this alien sky, you'll discover a landscape that is at once recognizable and completely foreign. Titan's surface has been sculpted by rivers and lakes, but these are not filled with water as we understand it. Instead, they are brimming with liquid methane and ethane, which flow through channels etched into the moon's frozen crust. These hydrocarbon seas represent a true wonder, a powerful demonstration of the chemical diversity that exists throughout the universe. The existence of these surface liquids is a definitive characteristic that distinguishes Titan from all other celestial bodies. Here on Earth, the water cycle governs our climate and geography. On Titan, a comparable cycle unfolds, but with methane and ethane substituting for water. This unique hydrocarbon cycle, featuring methane rainfall and ethane lakes, fosters a dynamic environment that may hold the very answers to understanding the intricate workings of planetary atmospheres. As we push past our conventional ideas, we are gradually learning what truly makes a planet or a moon habitable. And Titan's nitrogen-rich atmosphere and surface liquids present us with new and exciting possibilities. So, what are they? The nitrogen-dense atmosphere of Titan creates a natural shield against cosmic radiation, which is a major obstacle for space colonization. You might ask why we dedicate so much focus to solar radiation. The reason is both straightforward and deeply significant. Solar radiation is a relentless destroyer of living cells. Its impact isn't limited to microscopic organisms. It has a direct and harmful effect on us as human beings. Unshielded exposure to this radiation can lead to catastrophic cellular damage, threatening the fundamental structure of our biology and posing one of the gravest dangers to the health and survival of astronauts in space. Here on Earth, you and I are sheltered by our planet's atmosphere and magnetic field, but Titan offers its own form of protection. Its dense nitrogen atmosphere serves as a crucial shield,
making it a far safer destination for human settlement than the exposed surfaces of the Moon or Mars. Beneath this protective veil, you'll find a world defined by liquid methane and ethane, where vast lakes and rivers of hydrocarbons create a landscape that is both alien and full of potential.
Imagine a reality where our vessels navigate seas of methane, and the familiar water cycle is replaced by a completely new hydrocarbon equivalent. The existence of these surface liquids is far more than a scientific curiosity. It represents a vast, accessible resource. Methane and ethane can serve as potent fuels, offering a built-in energy supply for any future colony, and solving one of the most significant hurdles in space habitation: the need for a sustainable power source. Yet, Titan's generosity extends even deeper. Below its frozen exterior, you discover another critical resource: an abundance of water ice. The very compound essential for our survival is plentiful on this moon, locked away within its icy crust. This combination of accessible hydrocarbons and frozen water positions Titan as a remarkable repository of vital materials, providing the essential foundation for a self-sufficient human outpost far from our home world. Of course, this world of incredible promise also confronts us with monumental challenges. The environment is incredibly hostile, with temperatures that plummet to -290 degrees Celsius, a level of cold far beyond our natural experience. Adding to this complexity is the phenomenon of methane rain, a feature unique to Titan that presents another significant obstacle to survival. To overcome these immense difficulties, we must rely on the very best of human ingenuity and technology. Colonizing Titan isn't simply a matter of adapting. It demands a complete reimagining of how we live in such an extreme setting. You can envision habitats engineered to defy the intense cold, using advanced insulation and powered by Titan's own resources to create pockets of warmth and life. These advanced structures could be designed with systems that capture atmospheric methane and convert it into heat, effectively transforming a major environmental threat into a life-sustaining resource. Survival, however, is about more than just maintaining warmth. While methane rain poses a challenge, it could also be harnessed. Through sophisticated collection and filtration systems, this liquid could be repurposed not only for energy, but also as a fundamental raw material for producing essential supplies. Now, let's picture a fully realized human settlement on Titan, where magnificent dome cities blend scientific function with artistic design to complement the moon's unique environment. These interconnected habitats, built to withstand the cold and the methane showers, would stand as a testament to human resilience. Inside these domes, life would flourish, supported by hydroponic gardens for food, comprehensive recycling systems to conserve every resource, and shared spaces designed to cultivate a strong sense of community. Once you observe a thriving colony on Titan, it becomes evident that this moon is more than a new address for humanity. It's a nexus of scientific and economic opportunity. Its unique conditions and rich resources open up prospects we've only begun to imagine. The primary economic advantage of settling Titan comes from its enormous hydrocarbon reserves, which are not just fuel, but also valuable feedstock for advanced chemical synthesis, potentially turning the moon into an economic linchpin for interplanetary commerce. From a scientific standpoint, Titan is an absolute goldmine, with its complex atmospheric and surface chemistry providing unparalleled opportunities for research into organic chemistry and astrobiology. By studying its methane cycle and prebiotic environment,
You could uncover fundamental secrets about how life begins, not just on our planet, but perhaps throughout the cosmos. Furthermore, Titan's low gravity and accessible fuel make it an ideal launchpad for exploring the outer solar system and beyond. However, these incredible opportunities are accompanied by serious ethical responsibilities. As we prepare to colonize Titan, you and I must consider our duty in interacting with this new world. It is essential that we prioritize the preservation of Titan's environment, respect its distinct characteristics, and act as thoughtful stewards. Our approach must be that of guardians, not conquerors, as our actions on this world will ultimately reflect our deepest values and our capacity to balance progress with responsibility. As we bring this exploration to a close, let's reflect on what we've learned. We've seen how Titan's dense nitrogen atmosphere provides a natural shield against cosmic dangers, and we've journeyed across alien landscapes where rivers of liquid hydrocarbons offer the very resources needed to secure our future among the stars. Our exploration has also revealed the potential for vibrant human habitats, where ingenuity transforms extreme challenges into advantages for survival and growth. When you contemplate humanity's future on Titan, you are reminded that this great undertaking is about far more than achieving technological dominance. It represents a profound journey that will compel us to grow, to learn, and to cultivate a deeper respect for the vast and wondrous universe we inhabit. This endeavor is not just about finding a new place to live. It's about becoming a species truly worthy of the stars. And so, you are left to ponder a monumental question. What does the act of setting foot on Titan truly mean for the future of our species? And how will our endeavors on that distant moon ultimately shape our destiny across the vast, unexplored cosmos?